to a lecture on free fall. Okay, so what causes this ball to fall when I drop it? Well, we all know the answer. That's gravity. How does gravity work, right? So gravity is a force, and forces cause masses to accelerate. The force of gravity is directly proportional to the amount of mass involved. The two masses, of course, in this case, are the ball and the mass of the Earth. So when we look at this equation, we can see a couple things. First of all, the mass of the Earth is very large, especially relative to the mass of this ball, or even the mass of me, or the mass of something much larger. So because of that, the mass of the second thing, we can ignore it. We can also see that the radius of the Earth is very large, right? Because the Earth is huge. So the distance from the center of the Earth hardly changes if we're on the top of a building or we're at sea level. Because of this, so we're just going to approximate that as 10 meters per second per second. So what that means is when something falls toward Earth, it accelerates at 10 meters per second per second. So each second it goes 10 meters per second faster. And so to do a little experiment, my assistant Sean and I went to the track and went to the highest point of the back of the bleachers, and we dropped a ball out of the air. And we recorded two measurements. We recorded the time it took the ball to fall from his hand to hit the ground, and of course we measured the height of the point where we dropped the ball out of the air to the ground. And of course we call these two measurements the time and the distance, and they are of course related. They're related because the higher the distance, the longer it takes for the ball to hit the ground. And that relationship is what we're going to discuss today. Okay, so there's going to be two questions. The first is going to be, if I drop this ball, say from the top of a building, and I know that the building is 30 meters off the ground, how long will it take the ball to hit the ground? Of course, the converse to that question is, if I drop the ball off the top of a building, and the ball takes a certain amount of seconds to hit the ground, can I determine how tall the building is? But to answer that question, we're just going to look at our table and we're going to say, okay, well, initially the ball is moving 0 meters per second. After 1 second, it's moving 10 meters per second. So the average speed that the ball falls during the first second of free fall is 5 meters per second. After the first second, the ball is falling at 10 meters per second, and after the second second, it's falling 20 meters per second. So the average speed is 15 meters per second, which means that over that second, it will fall 15 meters. You can repeat this process on down the line and see that between seconds 3 and 4, the ball falls 35 meters. Between seconds 4 and 5, it falls 45 meters. And between seconds 5 and 6, it falls 55 meters. One last observation, which is just a little bit interesting. We say, okay, well, how far does the ball fall per second if we divide by 5? Because we see that during each interval, it falls by some distance, then it's always a multiple of 5. So if we pull that 5 out, we see that in the first interval, it falls 1 meter, and in the second interval, it falls 3 meters, and in the third interval, it falls 5 meters, and then in the fourth interval, it falls 7 meters. So we can see that the distance that it falls in each interval is just a walk through the odd integers, of course, multiplied by 5. What we're going to say now is, okay, our pattern is going to be that, for example, if the ball falls for 6 seconds, then how far did it fall? Well, ignoring the 5 at first, we're going to say it's the sum of the first 6 odd numbers times 5. And that's pretty easy to write up in Python. So now we're going to pull up our Python editor and we're going to write a script.
Okay, so first we're going to set up lists that correspond to our 3 attributes, acceleration, speed, and distance. And then you can see we're going to set up our lists for acceleration and speed which are pretty straightforward. Acceleration is always 10, and speed is 10 times x. And next, we're going to write a function that's going to allow us to calculate the distance traveled at time x. And we're going to do that, of course, by taking the sum of the first x odds. The way we take the sum of the first x odds is we iterate through the range from 1 to 2 times x, counting by 2, and each pass through the loop, we add the integer to our variable sum of the first x odds. After we've passed through the loop, we have to, of course, return 5 times the sum of the first x odds because, again, we factored out the 5. And of course, as we did for acceleration and speed, we can use a list comprehension and our distance from time function to calculate the distance traveled for all x values in our time list. Finally, we can use the enumerate function to simultaneously walk over the indices and the data in the acceleration, speed, and distance lists. And for each attribute, we can set the x and the y labels and plot the data. And finally, we can call plot.show to view our figure.
Okay, so if we look at our plots, we're going to notice a few things. The first thing is, of course, that gravity is pretty boring, right? Gravitational constant is 10 meters per second, and that's true during any interval in free fall. So the ball's always speeding up at 10 meters per second. And then, of course, the relationship between velocity and time is also not that fascinating. It's a straight line, because velocity is linearly increasing with time. Then, however, the distance that the object has fallen, that's curved. And if you know what the curve is, you might be saying to yourself, that looks familiar. If you don't know what the curve is, that's fine too, right? But we can see that it's a curve, and it's a curve because as the object speeds up, it goes faster and faster. So the distance that the ball has fallen after x seconds have passed is 5 times the sum of the first x odd integers. So what is the sum of the first x odd integers? Well, let's think about it. The sum of the first odd integer is 1. Not surprising. The sum of the first two odd integers, which are 1 and 3, is 4. And the sum of the first three odd integers, which are 1, 3, and 5, is 9. And if we add the next odd integer, which is 7, then we get 16. Of course, the sum of the first 5 odd integers, we have to add 9, and we see that that is 25. And you might be noticing a pattern here. And just in case we're not, we can redraw how the odd integers sum geometrically. So in this figure, we're going to see the odd integers being represented by balls. And we're going to add the first odd integer to the second. Then we're going to add the third. And then we're going to add the fourth. Then we're going to add the fifth. Then we're going to add the sixth. And here we see that the sum of the first x odd integers is just x squared. So the sum of the first 6 odd integers is 36. And we can see geometrically why that is. It's because starting at any perfect square, for example 4, to make the next square, you have to add the 2 units on the bottom, 2 units on the top. That's going to be even because it's a perfect square, but also the unit for the corner piece, or the one left over. Okay, so now that we've made that observation, this equation gets a little bit simpler. And we can say, okay, well, instead of saying 5 times the first x odd integers, we can just say 5 times x squared, where x is the amount of seconds that the ball has fallen. If we recall our original plan for how we thought about how the ball fell was to break it into segments of 1 second each. We could have just done the whole interval. So we could have just said, okay, well, the ball starts off with no velocity. After 6 seconds, it'll be falling 60 meters per second. The average speed over those 6 seconds will be between 0 and 60. It'll be 30 meters per second. And so it'll fall that for 6 seconds. So of course, 6 times 30 is 180. So that is actually the correct answer. And of course, we notice that if we divide 180 by 5, or 1/2 a, then we get 36. So, which is of course equivalent to 1/2 at squared. So we could have calculated it like this, but then we wouldn't be able to derive our nice formula and understand that the sum of the first x odd integers is always a perfect square. And so for those of you who have taken calculus, and even for those of you who have not, we can make one last observation when we look at our plots. And the observation is that our function that describes the distance traveled over time during free fall, which is described by 1/2 at squared, that function's derivative is the function that describes the velocity at a certain time. So a times t, and of course that function's derivative, or the first function's second derivative, is just a. It's just acceleration. Or going backwards, the integral of the function that describes the acceleration is the function that describes the velocity, and the function that describes the velocity has an integral that is the function that describes the distance traveled. So we see that there's this nice relationship between acceleration and velocity and distance. A really important relationship that you learn about in calculus is that the function for the acceleration, if we look at the area under the curve after a certain time, that area is given by the velocity function. And if we look at the velocity function, the area under that curve is given by the position or the distance function at any given time. So of course, the velocity tells us how the distance is changing, and the acceleration tells us how the velocity is changing. And that relationship there is what we learn about when we study calculus. So to recap, I really hope that was helpful. What we did today was we took a pretty easy problem, right? We took the problem of falling objects, or the free fall problem. We made a few approximations, and then we used Python to write a quick script because we initially approximated our equation with something that was a little bit unwieldy and contained a sum, and we didn't want to do that by hand. After doing so, we figured out that there is a nice closed form solution to the problem. We derived the formula. We made the observation that the relationship between these three quantities, acceleration, velocity, and distance, are related, and that each one describes how the other changes. And so indeed, we're now equipped with a function and also the knowledge in our head to calculate the distance of any building by dropping a ball off it. So I hope that's helpful, and I hope the tutorial was worthwhile.